Okay, let's dive right into this. Have you ever just looked at a massive cruise ship, I mean a real monster of a thing, and thought, how in the world does that not just sink? It's one of those puzzles that just seems to break your brain. But the answer is actually one of the most beautiful principles in all of physics. And today, we're going to break it all down.
And this, right here, is the core of the mystery, isn't it? You've got two things, both made of steel. One is absolutely gigantic, weighing hundreds of thousands of tons. The other is so small you can just pinch it between your fingers. And yet, the tiny little nail just plummets straight to the bottom, while the behemoth, it just sails on top. What is going on here?
To start figuring this out, let's think about a feeling we have all had. If you've ever tried to push a beach ball or even just an empty bottle under the water at the pool, you know exactly what I'm talking about. You feel this stubborn, invisible force pushing right back up at you. And the deeper you try to push it, the stronger that push gets. Well, that invisible push, it actually has a name. It's called the buoyant force, or a simpler way to say it is upthrust. And it's the force that any fluid, and I mean any fluid, whether it's water or oil or even the air all around us, exerts upwards on an object. This is the secret hero of our entire story. This upthrust is also the reason why things feel so much lighter in water. You might know this feeling if you've ever tried to lift something heavy out of a pool. While the object is underwater, it feels, manageable. But the second it breaks the surface, bam! All of a sudden you feel its true crushing weight. That's because when it was underwater, the upthrust was giving you a helping hand.
Okay, so we've established there's this upward force. We've all felt it. But that's not quite enough to solve our ship versus nail mystery. The really big question is, how do we measure it? How can we know exactly how much lift an object is going to get? Well, for that, we have to turn to a genius from ancient Greece.
And here it is, the big one, the eureka moment. This is Archimedes' Principle, and it is so powerful because it's so simple. The amount of upthrust pushing on an object is exactly equal to the weight of the fluid that the object pushes out of the way. Let me say that again. It's not about the object's own weight. It's about the weight of the displaced water. That is the key.
And what's so cool is how elegantly you can prove this. So imagine we take a metal block. Step 1, in the air, it weighs 300 grams. Simple enough. Then in step 2, we submerge it. And suddenly its weight on the scale reads just 200 grams. It's like it magically lost 100 grams. But of course, the water it pushed out had to go somewhere. In step 3, we see it spills into a little measuring cup. And if you weigh that water in step 4, well, what do you know? It weighs exactly 100 grams. The lost weight is the upthrust. It's just brilliant.
So, it all boils down to this. Floating and sinking is nothing more than a tug of war. That's it. On one side, you have the object's actual weight, thanks to gravity, pulling it down, down, down. And on the other side, you have the upthrust, the weight of that displaced water pushing it up. The winner of this battle decides everything.
And here are the official rules of that game. It's pretty straightforward. If an object's weight is more powerful than the upthrust it can create, well, it's game over. It sinks. If its weight is perfectly balanced with the upthrust, it'll float, but completely underwater, just kind of hanging out there. But if its weight is less than the upthrust, it'll pop right up to the surface and float with part of it sticking out of the water.
But what really decides who wins this tug of war in the first place? Well, it all comes down to one single, crucial property: density, which is just a fancy way of saying how much stuff is packed into a certain amount of space. If an object is denser than water, it's going to weigh more than the water it displaces, and so it's going to sink. So let's circle all the way back to our little iron nail. Solid steel is about 8 times denser than water. That means for its tiny size, it's incredibly heavy. So when you drop it in, the weight of that little piece of steel is way more than the weight of the tiny bit of water it pushes aside. Weight wins the tug-of-war, hands down, and down it goes.
Okay, but wait a minute. The giant ship is also made of steel. It should be just as dense, right? So why on earth doesn't its massive weight just pull it straight to the bottom of the ocean? And this, right here, this is the secret sauce. It's not about the material, it's about the average density. A ship, you see, is mostly empty space. It's basically a giant, cleverly shaped steel bowl. That hollow shape lets it push a colossal amount of water out of the way. And the weight of all that displaced water creates an enormous upthrust, more than enough to fight back against the weight of the steel. It's a man-made miracle of manipulating density.
So, we've cracked the code of the floating ship.
But this principle isn't just a cool party trick or an answer to a riddle. It is absolutely critical for some of the most amazing technologies and natural phenomena you see all the time.
I mean, just look at submarines. They are absolute masters of this principle. They have these special containers called ballast tanks. When they want to dive, they just open the vents and flood the tanks with seawater. This makes them heavier and increases their average density until they sink. And to come back up, they just blast that water out with compressed air, making themselves less dense, and the upthrust just shoves them right back to the surface.
Now here's a number that might just blow your mind a little bit. 90%. What in the world do you think this could be referring to when we're talking about things that float? It's the reason icebergs are so incredibly dangerous. You see, ice is only about 10% less dense than seawater. It's a really small difference. So because of that, for an iceberg to float at all, it has to be almost entirely underwater to displace enough water to support its own weight. And that means the vast majority of it, yeah, about 90% of that mountain of ice, is hiding beneath the waves.
So, let's end with a little brain teaser, just to see if you've really got this down. You have a glass of water, and there's an ice cube floating in it right at the brim. Now that ice cube melts completely. What happens to the water level in the glass? Does it go up and overflow? Does it go down? Or does it stay exactly the same? Think about the weight of that floating ice and the weight of the water it displaces. The answer is pretty cool.